All right, it is time to review intermolecular forces. So remember we had states of matter, solid, liquid, and gas, and we talked about it in the last video. In a solid, the intermolecular forces are strong. In a gas, the intermolecular forces are weak, and in a liquid, they're in between. So again, we can have changes of state. So if we change from a solid to a liquid, that means we've got to break some of those intermolecular forces. That's why it takes energy. If we change from a liquid to a gas, we've got to break some of those intermolecular forces. That's why it takes energy. Whereas if we go from a gas to a liquid, we're going to form some of those intermolecular forces. And when bonds form, energy is released. So ionic compounds or ionic bonds. So it's usually formed between a metal and a nonmetal, but we can have stuff from table E in there as well. But generally, strong, very, very, very strong attractive bonds. A lot of times it's described as a crystal lattice structure. They have very high melting points, very high boiling points, and if we have smaller ions, the bonds are stronger. So we have something like lithium at the top of the group compared to cesium, something down below, lower in the group. Lithium is going to be able to have stronger bonds because those ions are going to be able to get closer together because they're small. Okay, we have London dispersion forces. These are formed in any kind of covalent compound, but it's the only kind found in nonpolar. And these are very weak forces, which is why nonpolar compounds tend to have very low boiling points because it doesn't take a lot of energy to break those bonds. Dipole-dipole forces are in covalent, but only in polar covalent. The more polar the compound is, the stronger the dipole-dipole forces are. And the reason this happens is because in a polar compound, there's a partially positive section of the molecule and a partially negative section of the molecule. And those partially positive sections will be attracted to the partially negative sections, forming a stronger bond. Remember, an attractive force is strong. And then we have hydrogen bonding, which is a type of dipole-dipole force, but a really strong one. So it forms between hydrogen and one of three very electronegative elements, nitrogen, oxygen, and fluorine. So if it's hydrogen bonded with nitrogen, or hydrogen bonded with oxygen, or hydrogen bonded with fluorine, you will have hydrogen bonding. It explains the unique properties of water because hydrogen bonds are so strong. Water should not have as high of a boiling point as it does, but because it has hydrogen bonding, it has a high boiling point. And thank goodness, because we probably wouldn't be existing if it weren't for hydrogen bonding and the unique properties of water. So covalent bond versus the hydrogen bond. So look here. Inside the water molecule, there's a polar covalent bond between the oxygen and the hydrogen in one water molecule. When we're talking about the attraction between the hydrogen and oxygen of two different water molecules, those are the hydrogen bonds. All right, the strength of intermolecular forces. It determines properties like state of matter. Remember, strong intermolecular forces, solids. It determines melting points and boiling points. Strong forces, high boiling points. Low intermolecular forces, low boiling points. Stronger forces give you solids, high melting points, high boiling points. Weaker forces give you gases, lower melting points, and lower boiling points. So in terms of intermolecular forces, those London dispersion forces are the weakest. Then we have dipole-dipole. Then we have hydrogen bonds. And then ionic bonding in ionic compounds is kind of off the chart. It's even higher, okay? So London dispersion forces, weak as an intermolecular force. Hydrogen bonding, strong. So here's a nice little visual to help you remember that. Again, another little visual, no bond, dispersion forces, weak, dipole-dipole, stronger, hydrogen bonds, the strongest, even stronger than that would be what? Do you remember? Ionic. So solids have the most attraction. The particles are closely packed. Liquids have less intermolecular forces than solids, so the particles can flow. And gases have the least intermolecular forces, and the particles can move around independently. So if we look here, if we have a molecular substance, remember, molecular means covalent. Molecular means covalent. If we have nonpolar, which is symmetrical, the smallest ones will have the lowest melting points. The biggest ones will have a little bit more. And then if we're talking about polar, if there's no hydrogen bonding, the melting point is a little bit less than if you have hydrogen bonding. In fact, a lot less. But again, you can see the trend. Smaller will have less of a melting point, okay, compared to big. So the big ones will have more intermolecular forces and increased melting points. And that is intermolecular forces. I hope you learned something new today.